Okay, so hello and welcome back. So in this video we want to talk about exercises 15.2. So number one, you want to find the mean and variance for each of the data in 1 to 5. The mean and variance. So the mean and variance for each of these examples. So for example, let's say that you have 6, 7, 10, 12, 13. You have this data over here, 6, 7, 10, 12, 10, 12, 13, 4, 8, and 2. 6, 7, 10, 12, 13, 4, 8, 12. 4, 8, 12. Okay, so to find the mean of your data, well, you can of course add all of these numbers together and divide by the number of those numbers, and that gives you the mean. That's not very complicated, but let's form a table here and write them in ascending order. So I write my x sub i's over here, and you can go for example, 4, 6, 7, 8, 4, 6, 7, 8. So you have 1, 4, you have basically 1, 6, you have 1, 7, you have 1, 8, so 1, 2, 3, and 4, and then you have 10, 12, 10, 12, and 13. 10, 12, and 13. Ten is 1 times, 12 is 2 times, and 13 is 1 time. So I have 1, 2, 3, 4, 5, 7, and 8. 1, 2, 3, 4, 5, 6, 7, 8 observations, and 8 observations here, and this is your f of I. So now to find the mean of your data, you know that the mean of your data is equal to x bar, which is equal to sigma f of I x of I divided by sigma f of I. In both cases, in both of these sigmas, as I goes from 1 to n. Meaning that you can multiply your f of I into x of I, which is easy here. There is no need to do anything else really. So if I write f of I times x of I and multiply all of these together, I get 4, 6, 7, 8, 10, 24, and 13. And then what I can do is calculate sigma f of I f of I. Calculate sigma f of I x of I, which is equal to 10 plus 15 is equal to 25, 35, 55, 65, 65 plus 7 is equal to 65 plus 7 is equal to 72. Is equal to 72. So that's 72, and sigma f of I is equal to 3, 4, 5, 7, and 8. Right? So then x bar is equal to sigma f of I x of I, which is equal to 72 divided by 8, and that's equal to divide by 2, you will get 30, 35, 36, divide by 2, you will get 4, and 36 divided by 4 is equal to 9. 9 times 8 is equal to 72. So your x bar is equal to 9. And of course, if you just simply take a simple calculator and add all of these numbers together and divide by their number, for example, meaning that 6 plus 7 plus 10 plus 12 plus 13 plus 4 plus 8 plus 12, and divide by their number, which was 8, you would get a 9. So that's the mean of your data, meaning that you simply calculate the average of your data. Now, the next thing that you want to do, find the variance of your data. So the variance is nothing but the basically the average of the meaning that the variance is basically sigma basically f of I times x sub I minus x bar divided by sigma f of I. And that basically has been called sigma, that has been called basically lowercase sigma squared, which is basically simply called variance. And let me see if I'm not mistaken here. So sigma squared is equal to the same thing over here. Let me take this out, and then you have basically this is your variance, meaning that sigma squared is equal to 1 over n. So this is n. So 1 over n sigma x sub I minus x bar whole squared. Of course, this is supposed to be squared. And this is a squared because you want to get the because here you might get a negative number, so you want it, in order to get rid of the negative signs, you square it in order to basically have positive numbers over here, and then multiply it by the frequency of each x sub I, and then you add all of those numbers together divided by sigma f of I to get the mean of those things, and that's sigma squared. Now what this number actually is and what it means is that basically this is a measure of how scattered your data is from your x bar, meaning that suppose that, for example, you have all of these observations here, for example 4, 6, 7, 8, 10 through 13. You have all of these numbers here, 4, 6, let's say this is 4, this is 6, 8, 10, for example, 12, and 14. And your observations are 4, 1, 6, 1, for example, 7, 1, 8, 1. I don't think we had 7 over here. We had 7 over here. 8, 1. And you had 10, 1, you had 12, 2, so we have 2 observations here, and you have 13, 1. The mean of this data was 9. X bar was 9, so this is your X bar. So now, in order to get a feel for how scattered your data is, you take, so these are your X sub I's. These are your x sub i's, and this number over here is x bar, the mean of all of these observations. Now what you're doing here is that you're taking each x sub I and calculating the difference of x sub I and x bar, meaning that, for example, x sub I minus x bar, which is in this case, for example, a negative number. Or in this case, for example, you take this x sub I and subtract from that your x bar, which is in this case, for example, a positive number. And and of course you're multiplying f of I by that, because sometimes, for example, as you can see, there are, for example, 2 x of i's. For example, in this case you have this x of I and this x of I. Because you don't want to do it twice, so you just simply can multiply it by f of I to take care of the frequency of your data, meaning that if observations basically, if distinct observations basically repeat themselves. And well, before adding those numbers together, you are actually multiplying, you're actually raising this x of I minus x bar to the second power. Meaning that, for example, if this distance is, for example, whatever, for example, 3 units, 4 to 9 is basically 5 units, for example, then this number is going to be, for example, a 25. And 25 times, for example, the frequency, take the frequency, for example, 1 here, that's going to be a 25. And then you have another observation, for example, over here. Again, you're taking that distance and then raising it to the second power, and then basically multiplying by the respective f of I. And once you do all of that, meaning that once you've taken care of all of your observations, then you divide the whole thing by sigma f of I, meaning divided by the number of the observations that you had. And this is, well, I don't know what to call it. It's a weird thing, really. But it gives you a measure of how, for example, how your observations are scattered around the mean, right? I mean, I wouldn't do such a thing. Maybe so let me actually go and read through the part that we did over here. You have standard deviation. So what they're doing, first of all, this kind of thing, we did it because basically because of the limitations of the mean deviation. We said that the mean was not a very good basically measure of central tendency. It had all of these problems, like, for example, when the degree of the variability of the data is high, then the median is not a good representative central tendency, and then the mean deviation about the median calculated for this series doesn't make much sense, or that you cannot rely on it. And then we said that the sum of the deviations from the mean, basically the minus sign ignored, is more than the sum of the deviations from the median. Therefore, the mean deviation about the mean is not very scientific. And in many cases, mean deviation may give unsatisfactory results. Also, mean deviation is calculated on the basis of absolute values of the deviations, and therefore cannot be subjected to further algebraic treatment. So this implies that we must have some other measure of dispersion. So, and that's basically why we came up with this whole business of sigma and sigma squared and variance and standard deviation and the whole story. Now, in order to solve this problem, we came up with we came up with this idea of basically all of these observations as x1, x2, x3, and all the way up to x of n, with their mean as x bar. Then we said that that basically the sum of all of those, the sum of basically all of the distances of these observations from the mean would be x1, for example, minus x bar whole squared that says that another way to overcome this difficulty, which basically so basically to take care of the mean deviation, we took the absolute value of, for example, x of I minus x bar, for example, and basically we took the absolute value, because otherwise basically some observations might actually cancel each other out in the meaning that, for example, you could have, for example, two observations. Let's say that this is x bar and this is x1, and for example this is x2. And so if x1, for example, is equal to negative x2, then these two will cancel each other out, then and then some x3 is equal to negative x4, and then these will cancel each other out, and so on and so forth. And then you will run into the problem of basically coming up with a zero, which is not what you want, because you want some number to be a good representative of the dispersion of your data. So then, in order to solve that problem, and we wanted to not use the absolute value function, because the absolute value function basically in the absolute value, then the algebraic sign of the numbers are lost, and so then the numbers cannot be treated algebraically anymore once the number comes out of the absolute value function. So then, in order to do that, which is still not reason enough for me, but let's go with the reasoning. Let's see where we get. So then we came up with the idea of getting rid of the absolute value function, and then instead squaring all of the distances. And then we came up, for example, with x of 1 minus x bar whole squared plus x of x2 minus x bar whole squared plus all the way up to, for example, x of n minus x bar whole squared. And we call that, for example, sigma x of I minus x bar whole squared. And of course, if this sum is equal to 0, that means that all of the observations are actually equal to the mean, right? And then if, for example, if this sigma x of I minus x bar is small, this indicates that the observations are very close to the mean and has a lower degree of dispersion. And on the other hand, if the sum is large, then the dispersion of the observations is there is a higher degree of dispersion of the observations from the mean. And then we came up with the question that if basically sigma x of I minus x bar whole squared is a reasonable indicator of the degree of the dispersion or scatter. And we came up with these two examples, And we saw that in those examples, this basically we had basically two basically sets A and B, and we said that we saw that basically in set A, although the dispersion was the degree of dispersion was lower, the number that we got was higher, and vice versa. In B, the dispersion was higher, and then the number that we got was lower. So that meant that basically we could not use this measure over here. This would not serve us as a good measure of dispersion, right? Of course, if you want to have more details about what I'm talking about right now, you can go back and of course watch the videos that we talked about these in detail. I'm just walking us through the reasoning right now. And so basically, thus we can do, and then we said that thus we can say that the sum of the squares of deviations from the mean is not a proper measure of dispersion. To overcome this difficulty, we take the mean of the squares of the deviations, meaning that instead of writing the sigma x of I minus x bar whole squared, we wrote this expression as sigma basically x of I minus x bar whole squared divided by sigma f of I, by sigma f of I. And then you can call, of course, sigma f of I, you can call it n, so you can write it as sigma x of I minus x bar whole squared over n. That's basically how we wrote this thing. And then we called this basically so then we said that thus we can take basically 1 divided by n times sigma x of I minus x bar whole squared as a quantity which leads to a proper measure of dispersion. This number, that is the mean of the squares of the deviations from the mean, is called the variance. We call this the variance. It's called the variance, and we denoted this by sigma squared. So, and then we said that then the variance of n observations the variance of n observations x1, for example, comma x2, comma x3, all the way to x of n, is given by sigma squared is equal to 1 over n times sigma of basically x of I minus x bar whole squared. That was basically the variance. And then based on that, we defined some other quantity which was called, or some other basically measure which was called the standard deviation, which was just simply the square root of this whole thing, meaning that instead of sigma squared, if you write sigma, then you can write it as the square root of 1 over n times sigma of x of I minus x bar whole squared. And we call this basically standard deviation. Standard deviation. Okay. Now and then of course there is the problem of basically the frequency of your data, in which case you can simply write these two as, for example, sigma squared. You can write it as sigma squared is equal to 1 over n, for example, times sigma of f of I, at basically multiply this f of I by x of I minus x bar whole squared, in case there is some frequency for your data. And then based on that, so this becomes again your becomes variance, and standard deviation becomes the square root of 1 over n sigma f of I times x of I minus x bar whole squared. That is basically what we talked about. So this is some, I don't know, it's a weird measure of, you don't really know what this is showing you. I think the only way to make sense of it is just to somehow make sense of get a feel for the number that you get from this formula. Otherwise, well, but this is now something basically standard in mathematics. I wouldn't really want to argue with this really, because it's now everywhere. And then that is basically the whole story behind this. Of course, we talked about this extensively and in detail, but then I wanted to just go through the process one more time to see if I could make sense. Of course, you would understand, you do understand this whole process, but it's not, I mean, it's a little bit messy, you know. Anyway, but well, again, I don't really want to argue with this, because now it's everywhere. It's standard mathematics. There is no point in arguing with that. Well, at least the least that you can do, you need to understand it well, because everybody else would be talking about the same thing in terms of the same rules and regulations. So you don't want to. At least you need to understand it. Okay, so that's the whole story. Now, what's important here is that now suppose that you want to find the variance of your data, of this data that you have over here, which is basically sigma squared, sigma f of I times x of I minus x bar whole squared over sigma f of I. And of course, in order to do that, you need to calculate basically x of I minus x bar. So x of I minus x bar whole squared, which would be basically, in this case, now x bar is equal to 9, so 4 minus 9, for example, is negative 5, which is negative 5 squared is 25. 6 minus 9 is equal to negative 3. Negative 3 squared is equal to 9, positive 9. That's 7 minus 9 is equal to negative 2 squared is equal to 4. Negative 1 squared is equal to 1. 1 squared is equal to 1. 3 squared is equal to 9. And 4 squared is equal to 16. And I'm going to just simply take a screenshot here. Put it over here, and then erase this thing, because I need the space here. And so now I want to calculate basically f of I times x of I minus x bar whole squared. So that's 1 times 25, for example, is 25. 1 times 9, all of these are 1, so I just write them as they are. 4, 1, 1, and this is 2 times 9 is equal to 18, and 1 times 16 is equal to 16. And then you want to calculate sigma f of I times x of I minus x bar whole squared, which is all of these numbers added together, which is, that's a 13, 14, 15, 15 plus 25, and then you have basically 20, 18 and 16 is 14 and 34. So you have a 10, 14 here, 1. So you have 2, 4 and 74. There was 74 there, and then you have and sigma f of I is equal to 8. So now your variance, which is nothing but sigma squared, is equal to basically sigma f of I times x of I minus x bar whole squared over sigma f of I, which is the same thing as 74 over 8, which is the same, 74 over 8 is basically 35, 37 over 4, right? 37 over 4, and that is basically 37 over 4 is the same thing as, I don't know, 9 times 4 is equal to 36, remainder 1, and then 0.00, 2 times 4 is equal to 8, 2, 0, 0, 5 times, so 9.25. I think that is the answer there. Okay, that was question number 1. That was question number 1, exercise 15.2. 9.9 and 9.25. So that is basically the answer there, and that's the whole story there. Okay, so now question number 2 is okay, so now the mean, now the next question is let's see. So the next question is basically you have the first n natural numbers. You have the first n natural numbers. If you have the first, basically, well, the first n natural numbers would be 1, 2, 3, all the way up to infinity, right? And that's equal to the set of n, which is basically all of these numbers. These are the natural numbers. And if you want to find the mean of these numbers, of course it's going to be equal to sigma, it's going to be equal to sigma f of I, for example, x of I, divided by sigma f of I, and that's equal to x bar, right? Now, your sigma f of I is of course n, then the number of, basically you have n natural numbers. So you can write this as n, and sigma f of I x of I, of course your f of I in all cases, basically since the numbers don't repeat themselves, you can just simply write this as sigma f of I. I'm sorry, sigma x of I. And since you're dealing with sigma x of I, and you're talking about natural numbers when I goes from 1 to n, and you're talking about the first n natural numbers, the sum of the first n natural numbers is n times, I don't remember that. You see, basically when you have, for example, there is something called an arithmetic progression. There is something called an arithmetic progression, and what that is that basically when you have a progression is a bunch of numbers that progress. So, for example, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So you want to find the sum of these numbers. So of course you could add all of these numbers together, meaning that 1 plus 2 is equal to 3, 3 plus 3 is equal to 6, plus 6 plus 4 is equal to 10, 10 plus 5 is equal to 15, 15 plus 6, and so on and so forth. But, well, you can do this for 10 numbers or for 20 numbers, but then when your numbers go from 1, 2, 3 all the way up to, for example, 200, then of course you cannot sit and calculate the sum of the first 200 natural numbers. That's not, well, that's possible. Mathematicians used to do this, for example, like, I don't know, around 100, 120, 130 years ago. I saw this movie, The Man Who Knew Infinity. It's about Ramanujan, who went to London and, not to London, to England somewhere, and he became a fellow member of the Royal Society in London, and he was a mathematician, of course. So back then, there were no such basically formulas in mathematics, like, for example, the sum of the first n natural numbers, and so on and so forth. So, and there were of course no calculators and no such things. So people used to, if they needed to calculate something, so they had to basically sit and calculate for, I don't know, even over a week or so in order to get the sum of, for example, some number of numbers, for example. And then Ramanujan comes along and he comes up with all of these formulas, but the problem with him was that he had this habit of not proving things. He didn't believe in proofs. And it seems that he couldn't even prove most of his formulas, he couldn't even prove them. But anyway, he had all of these notebooks full of basically formulas and everything about the infinite series and all those kinds of things. And so then everything's kind of started from there, and then people started even working on Ramanujan's work, and mathematicians started proving his work. And some of his formulas, for example, there were something that he did in mathematics, like, for example, over 100 years ago, and now these formulas are being used in physics, for example, in order to understand black holes and that sort of thing. So, but back then these formulas were not like something that you ordinarily would read in a school mathematics book, something like that. So now, in order to basically add these numbers together, there is something called an arithmetic progression. And an arithmetic progression is basically a progression of numbers in which, for example, you get, you you add a 1 to this number and you get a 2. You get a 1 to this number, you get a 3. You get a 1 to this number, you get the next number, and so on and so forth. So that's called an arithmetic progression. On the other hand, for example, if you have 1, 2, for example, 4, 8, 16, 32, and so on and so forth, then this is called a geometric progression. This is called a geometric progression. And a geometric progression is the kind of progression where you multiply this number, for example, by a 2 to get the next one. Multiply this number by a 2 again to get the next one. Again, multiply by a 2 to get the next one, and so on and so forth. And of course, a geometric progression could be in the form, for example, 1, 3, 9, for example, 27. 27 times 3 is equal to 81, and so on and so forth. So now, basically what we want to talk about is how to, and of course in arithmetic and arithmetic progression, it doesn't necessarily have to be 1, 2, 3, 4, 5. It could be, for example, 1, 3, 5, 7, for example, 9, 11, and so on and so forth. That's also an arithmetic progression. Because you're adding a 2 to this, again, you're adding a 2 to this, you're adding a 2 to this, and so on and so forth. That means that the common difference of each of these terms is equal to 2, 2, 2, and so on and so forth. And of course, it could be also, for example, it could also be, for example, you could also subtract, for example, a 2 from these numbers, meaning that you could start with a 1 and then minus 2 would be a negative 1, minus 2 would be a negative 3, negative 5, and so on and so forth. That you could do as well. These are all basically arithmetic progressions. Now, I don't want to get into much detail of these, but if you want to, for example, add these numbers together, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there is a formula for the arithmetic progressions, and you call it, for example, S of n, which is the sum of the n terms of an arithmetic progression. That's equal to that's equal to a plus n minus 1 times, no, a plus, that is a plus n minus 1 times d. That is basically the a of n. I'll tell you what I mean by a of n. But then there is something else, which is s of n. S of n, which is basically, let me see if we can find it here. So if you search for the sum of first of n terms of an AP, so S of n, that's basically the formula. S of n is equal to n divided by 2 times 2a plus n minus 1 times d. And a of n is equal to basically a plus n minus 1 times d. So a of n is equal to a plus n minus 1 times d, and S of n is equal to n divided by 2 times 2a plus n minus 1 times d. Now, what that is, let me see if I wrote that right, 2a plus n minus 1 times d. So this is basically, this gives you the nth term in an arithmetic progression, meaning that, for example, in this arithmetic progression, the first term is called a. In this formula, a refers to the first term here. D is your common difference. D is your common difference which is basically the number that you add to each term to get to the next term. So for example, over here, your d is equal to, for example, 1. And of course, n is the number of terms that you have. So for example, over here, n is equal to 10 because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 terms. So that means that, for example, in this arithmetic progression, if you want to know what is the fifth term, for example, which is denoted by a of 5, then a of 5 is going to be equal to a plus a is equal to 1 plus n minus 1, which is 10 minus 1, which is equal to 9 times d, which is d is equal to 1, which is equal to 1 plus 9, which is equal to n minus 1 times d. D is equal to 1, n is equal to 9. Oh, there's something wrong here. N is equal to okay, sorry. So n is actually here is equal to 5. So a plus n minus 1 times d, a is equal to 1, for example, and n minus 1 is 5 minus 1, which is equal to 4 times, basically d is equal to 1 here, because your common difference here is 1. So that's equal to 1 plus 4, which is equal to 5. That means that a of 5 is equal to 5, which is actually 5 here. Now, and of course, if you want to calculate the s of 10 here, for example, that would be basically the sum of the first n terms in this arithmetic progression. So you can write it as 10 divided by 2 times 2 times a, which is 2 times basically 1, plus n minus 1, which is equal to 10 minus 1 is equal to 9 times d, which is equal to 1. So that's equal to 5 times 2 plus 9, which is equal to 5 times 11, which is equal to 55. That means that if you add all of these numbers together, you will get a 55. And, well, it works like magic. It works for 200 numbers, 300 numbers, 500 numbers, 1000 numbers. It doesn't matter how many numbers you have. Now, suppose that you have, so now let me write these formulas here and then we will. So we said that in the case of an arithmetic progression, a of n is equal to a plus n minus 1 times d, and s of n is equal to n divided by 2 times 2a plus n minus 1 times d. N minus 1 times d. So what that means is that, for example, over here, if, let me rewrite this again, or let me rewrite this, not that the again part is not required. So if I have some series like some arithmetic progression like 1, 2, 3, 4, and so on and so forth, n terms. So over here, you see that first of all, this is an arithmetic progression because every term you can get every term you can get if you add 1 to the previous term. Add 1 to the previous term, you get 2. Add 1 to the previous term, you get 3, and so on and so forth. And so in this arithmetic progression, your a, which is the first term, is 1, and your common difference, which is d, is equal to 1, because you add 1 to each of these terms to get to the next term. So now, if I were to find the sum of n terms of this arithmetic progression, which would be the sum of the first n natural numbers, that would be s of n is equal to n divided by 2 times 2a, which is equal to 2 times 1 is equal to 2 plus n minus 1 times d, which is equal to 1. So that is simply just times 1, which basically gives me n divided by 2 times 2 plus n minus 1, which is equal to n divided by 2 times 2 minus 1 is equal to 1, so that's n plus 1. So that gives me n squared by, that gives me n times n plus 1, n times n plus 1 divided by 2. So S of n is equal to n times n plus 1 divided by 2. That is the sum of the first n natural numbers. That's how you calculate that. And of course, if you search on the internet for the sum of first n natural numbers, you will see the same formula: n times n plus 1 divided by 2. Meaning that over here the sum of, for example, sum of first natural natural numbers, you see over here what it gives you is n times n plus 1 divided by 2. N times n plus 1 divided by 2. So if you understand basically simple things about arithmetic progressions and geometric progressions, you can calculate all of these by yourself without having to memorize all of these formulas. Now, what's important here is basically, so we said that S of n is equal to n times n plus 1 divided by 2. So I can now get rid of all of these. So now I can come over here and I wanted to calculate the mean of all of these numbers. The mean of all of these numbers. So the mean of all of these numbers is first of all, the sum of all of the numbers divided by the number of them. So sigma x of I, when I goes from 1 to n, as we calculated here, is n divided by n times n plus 1 divided by 2. And then you have to divide that by n, because that's the number of, that is the number of those terms, which is the same thing as basically n times n plus 1 divided by 2n. These two you will cancel out, and then you'll have n plus 1 divided by 2. That is the mean of, that is the mean of the first n natural numbers. That's that. And now to find the variance of such numbers, we said that the variance is sigma squared, and that was equal to basically well, I keep forgetting formulas. That we said that that's equal to, that is equal to basically 1 over n sigma, well, the difference between x of I and x bar, and you take the average of that, right? And of course you have to raise that to the second power because of the weird part of the formula. So sigma squared is equal to 1 divided by n times sigma, basically f of I times x of I minus x bar whole squared as I goes from 1 to n. That is called variance. Sorry. That is called variance. So now what you need to do here is first of all, the x bar part, we calculated that to be n plus 1 divided by 2. So you can write this as, and of course, you know that in the case of these numbers, your f of I is equal to 1 in all cases. The numbers don't repeat themselves. So you can write your sigma squared as basically 1 divided by n times basically sigma of basically x of I minus x bar whole squared as I goes from 1 to n. Now x of I minus x bar is going to be basically, in the case of natural numbers, x of I is going to be, for example, 1 minus, for example, x bar whole squared. And then you have to add to that 2 minus x bar whole squared, 3 minus x bar whole squared, and so on and so forth. Which is going to be I don't know how to calculate that. Let me see how they have solved this problem. Okay, so now one thing that I wanted to mention here is that if you ever basically feel the need to find the solutions that you're looking for in the book, you can always go to this website. It's a great website, tiwariacademy.com, and you have all of these basically solutions here. So these are the NCERT solutions, which is basically the books that we are using here. So for example, this is class 6, class 7, class 8, class 9, class 10, class 11, and I don't know what these are. Answer, I don't know, sets, relations. But this is anyway not related to what we are doing right now. Probably they have, I don't know, copied some part of the book and put it somewhere, something like that. But then, for example, for class 11 that we are currently doing, you can go to mathematics, for example, and you have all of these chapters over here. See, you have 16 chapters over here. And the 16 chapters, for example, chapter 15 is statistics solutions. And then you have, for example, exercise 15.2. And then you can see all the solutions of these exercises, for example, question 1, question 2, and so on and so forth. And that way you can get basically all the solutions if you ever need them. Now,